MDM4U 4.3 Permutations with some identical items. We've learned how to solve problems with distinct objects. So if all items are distinguishable, how many ways can you rearrange the letters, for example, A, B, C, and D? Well, since all of them are being used and there's no repetition, for the number of choices for the first letter is 4, then the next option is 3 because there's one less, and then so on. 4 times 3 times 2 times 1, which can be summarized as 4 factorial. But if we have a set of objects where some of them are indistinguishable, for example, in this case we have 3 C's, we can apply the following formula. The number of permutations of a set of n objects containing A, identical objects of one kind, B, identical objects of a second kind, and C, identical objects of a third kind is given by n factorial divided by A factorial, B factorial, C factorial. And we'll see that for this example, n represents 1, 2, 3, 4, 5, 6 objects. And our identical objects, there's 3 C's. So we divide by 3 factorial to get our solution. Last example, how many ways can you rearrange the letters A, B, B, C, 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 C? So notice there's repetition of B's and repetition of C's. In the numerator of our formula, we're counting the total number of objects. So 1, 2, 3, 4, 5, 6, 7 items. And the 2 factorial in the equation represents the 2 B's, which are indistinguishable. And then the 4 factorial represents the C's, which are repeated or indistinguishable. So that is how we use this formula. But let's investigate using enumeration to check to see why this is true. So enumeration is where we list each and every single possible outcome. For ABC, we could say that this is 3 factorial or 6 different outcomes. Using enumeration, we'll look at each and every single rearrangement, and there you have it. But if we were to have A, B, B, we have some cases that would be indistinguishable. If we were to give a subscript as a name to both the first and second B, we can't really tell between when we have B1 and B2 switched. And the number of ways that we can switch or rearrange these values if they were different or unique would be 2 factorial or 2. B1, B2 or B2, B1. So that's verified for this case. Next, for A, B, C, D, there are no identical items, so we can rearrange 4 items 4 factorial ways. That's a total of 24. If we were to have one pair of identical items, C and C in this case, now we can rearrange these right here in 2 factorial ways. Either C1, C2 or C2, C1. So therefore, we divide the total number of cases by 2 factorial, which is 2. Because for every single permutation, say for example this right here, where we have A, B, C, C, we have to eliminate one of those cases. We have half of them being accepted. Next, A, C, C, C. So an item is indistinguishable 3 times, or 3 identical items. And logically, you could think the only cases that would count would be where is A positioned, the first, second, third, or fourth place. That's what we see in our solution. And the number of ways in which 3 items can be rearranged is 3 factorial. So when we divide the total 4 factorial by 3 factorial, we get 4 factorial divided by 6. And notice that there is 1 acceptable solution for every 6. Next, with 2 pairs of identical items, AA and BB, there's 4 items, 1, 2, 3, 4, divided by 2 factorial and 2 factorial, because for every permutation that exists, these can be rearranged in 2 factorial ways, and for every permutation that exists, these can be rearranged in 2 factorial ways. So there's only half of those cases for each being accepted. So that's a quarter of the total.